in the existing concrete structure. So let's talk a little bit about some of the repair strategies if your post-tensioning tendon is damaged for whatever reason. And in my experience, there are a lot of reasons why your post-tensioning tendons can be damaged. It could be as a result of impact, fire, corrosion, saw cutting. You know, someone cuts into a slab and they didn't know it was a post-tension slab. Or you can have blowouts that occur perhaps due to green concrete while stressing. And then you can have damage as a result of chipping. You know, someone takes a chipping hammer and chips into the slab and hits a tendon where they otherwise thought there would be no tendon. Now, when you have this type of damage, there's really three different things that can happen. Actually, there's a fourth thing. Number one, which is not here, is that you can always do nothing, right? If you find that your system or your slab or your beam has enough residual capacity, then there's always the option of doing nothing. Now, if you find that there is a deficiency, then there's a couple of different options, and let me walk you through those. So one of them is detensioning the tendon itself, and I'll talk about how to do that just to create a safe environment where there perhaps is no deficiency. Then I'll talk a little bit about full tendon replacement. While it being very rare, I'm going to walk you through how this is done in a safe manner. And then the last one that I'll talk about is partial tendon replacement. And you would do this because you have a tendon, for example, that's only damaged in the exterior bay due to environmental conditions. And you don't want to replace the parts of the tendon that are in good condition. So I'm going to talk to you about some of the different tools and techniques that you can use to just replace one part of a tendon if it should be damaged. And I'm going to use some of the nomenclature or some of the buzzwords from the PT industry about some of these different types of hardware, stressing couplers, you know, torque stressing couplers, center stressing. I'm going to show you how those can be used. So first, let's talk about detensioning a post-tension tendon. Now, the reason why I want to spend a moment on this is because for post-tensioning tendons, you have a piece of steel that's under high tension. And as a result, it could create an unsafe environment if you have a dramatic release of force. So to detension the tendon, there's two techniques. One is that you can use a grinder. So you can use your standard grinder, and you would cut one wire at a time. So this 7-wire strand has 6 smaller wires that are helically wound around the center wire. We call that the king wire. So normally you would cut all of your exterior wires first, and then you would cut the center wire. And the concept behind this is that you're gradually releasing the pre-stress force, theoretically 1/7 at a time. The other way of detensioning a tendon is to use an oxyacetylene torch. And this concept is pretty straightforward. Basically, if we take high temperature of heat and we wave a torch over top of a bare strand, that strand will start to elongate. And while it's elongating, you're slowly reducing the pre-stress force within that tendon. Now, there's one other point here that's important about detensioning bonded tendons that I want to speak about, and it has to do with whether or not the system is fully grouted or not. And the reason why I say this is because if you have a tendon that is partially grouted or it's ungrouted fully due to oversight or poor workmanship, when you go in to cut these tendons, you're going to get a dramatic release of force. And when it comes to doing a repair, you need to understand whether the strands are fully grouted. Now, when I say that, your first thought would be, well, Clyde, it's a grouted system. Why wouldn't it be? But we know in different parts of the world, the workmanship quality can vary. And so prior to doing any type of repair, and I'm going to say this multiple times throughout this presentation, you must make sure the tendon is fully grouted, because you may find that that is not always the case. So let me talk a little bit about full tendon replacement. Now, as I mentioned on the previous slide, this is something that's pretty rare. In my career, I've only done this twice. However, when it's required, it's really an extreme case, and you need to understand the different steps of doing it. So in this graphic that you see here on the left-hand side, what you see is this is a ramp or a car park that's uncovered. And for this particular ramp, the post-tensioning tendons were severely corroded. And so the owner was thinking, hey, what should I do? Should I completely demolish this ramp? Or is it possible to fix it in place? So the solution here was actually to remove the damaged tendons and to actually replace them in the same trench with new tendons. So let me walk through how you would do that. So this is a very interesting case study that I wanted to share. So number one, you would start with shoring the slab. Obviously, when you're going to be removing primary reinforcement, shoring is always going to be required as a first step. And then the next thing you do is you would create an open trench around the post-tensioning tendon. And we know post-tensioning tendons are normally spaced maybe about 1 meter on center. So once you use non-destructive equipment to find those tendons, then it's pretty easy to find all the remaining tendons. So once you open up the slab and chip open the trench, then you would remove that corroded tendon. And then in that same space, you would replace with a new tendon. Now, if you look at my graphic at the top, what you see here is, this is the trench that was created when we removed the existing tendon. You have to chip almost full depth at the low point between your supports. And then over your supports, you have to chip minimal depth. But the basic concept here is that you would use this same area of chipped concrete to reprofile your new post-tensioning tendons. Stress once the concrete reaches the required strength. Now, there's one other caveat to this that I wanted to mention, and it may be an oversight for an inexperienced designer, is that typically in a PT slab, you have tendons running in both directions. Whether it's a one-way slab or a two-way slab, typically tendons are running in both directions. So in this scenario where I'm creating these trenches full length of the ramp, I have to be concerned about the transverse post-tensioning and the effect of the slab, considering that I've removed these trenches. What we don't want to have happen is remove too much concrete so that the transverse PT becomes unstable and causes these trenches to close in on each other, which would be a disaster. So what you may have to do is you may have to create these trenches, and you may have to do it in phasing so that you don't create a problem in the opposite direction. Now let's talk a little bit about fire. This graphic might look familiar to most of you who've been in the region for some time. This is a tower that caught fire about 5 years back. And there was damage over 63 floors, 63 floor PT slab, but there was damage primarily from the 7th floor to the 56th floor. And there was all kinds of varying degree of damage. There was damage to walls, to beams, and to slabs. So what I want to focus on is damage to those slabs and how you would consider the remaining capacity for fire damaged PT tendons. So one thing about PT tendons that we know is that PT tendons lose strength faster than rebar. That's for two reasons. One is due to the metallurgy, but secondly, you have 6 wires spin around one single king wire, and because of this interstitial space between these wires, it has a tendency to heat up faster and lose strength prior to that for using the same temperature for mild steel. So when it comes to analyzing a fire damaged slab, you have to look at two effects. One is you have to look at ultimate strength, and the second you have to look at serviceability. So from an ultimate strength standpoint, what we assumed is that the existing post-tensioning had 0 residual capacity, because it's hard to determine exactly the extent of the damage. You probably have 50%, 25% remaining capacity, but there's really no scientific way to determine exactly what that residual capacity is. And so to be conservative, when looking at ultimate strength, we assume that the existing PT had 0 capacity. Now, from a serviceability standpoint, it's actually a little different. And what I mean by that is from a service standpoint, we know that the tendons that were affected by fire have some effect on the slab. Generally it's not 0. But one thing that's interesting about a PT slab that you have to be mindful of when you're designing it is that you have to look at the amount of pre-compression and uplift created from the post-tensioning tendons. Too much pre-compression can lead to restraint cracks, and too much uplift can actually cause a stress reversal where you crack the top of a slab at mid-span. So considering these two effects, for service check, we actually assumed that the existing tendons were fully effective, meaning the pre-compression and uplift were effective, and then we combine that with the new tendons. And then we looked at the combined effect of both of those tendons when we checked service. And we also did our checks for stress reversal and pre-compression. So this is a really important point to make note of here, because in a fire damage slab, you have to have different considerations whether you're checking strength or service. Now I have a couple of nice graphics that I wanted to share with you that I thought will be quite interesting. You know, when you're working on a damaged slab, and most of the damage, you know, when there's a fire, the flames go up and the damage is normally primarily focused on the soffit, right? And so in order to do a repair, you need to shore the slab. But how can you shore the slab if the fire damage area is, you know, directly above you? So to shore the slab, here in this graphic, you see a shoring system that's actually from the top of the slab, using this type of framing that actually has tie rods running through the slab and supporting it, and then the reaction actually going back to the surrounding walls. So this is one way of shoring the slab from the top. And then below that, you see where there's a new trench put in for the existing PT. Basically, we left the fire damage PT in place, and we created new trenches, and we profiled the tendon in those trenches. And then to the right and left, to the right, to the far right, you have the stressing end. We call this stress pocket in the US, or here we call it a pan box. And then to just below that, the dead end, this is the non-stressing end of the new post-tensioning tendon. So this kind of gives you a concept of how you would deal with the tendons and how you would actually implement the repair. Now let's talk about another technique using a torque stressing coupler. Now this graphic you see in the far left, what you see here is this is a overhead bridge crossing a road below. This actually was taken on a project in Florida, South Florida, on the Florida Turnpike, if you're familiar with that. And during about it was like the mid-2000s, there was a lot of construction in South Florida, a lot of construction vehicles running up and down the turnpike. And from time to time, the equipment on the flatbed trailer was taller than the maximum height allowed under the bridge. And when that happens, you actually have damage to the overpass, but primarily the damage is focused on the fascia girder, which is the exterior-most element of the bridge above. And so what you see here is a bridge that's been damaged by overhead vehicle. This is an AASHTO beam, or we can call it a pre-stressed beam, and you see several wires that were broken. And so the question here is, what do? Do you replace the beam, number one, or do you try to fix it in place? So let's talk about how you would try to fix it in place. So the first step is any strands that are hit from the impact, we would cut those out. Why? Because when you connect onto a new piece of strand, you need to have a good piece of strand to grab a hold of. You don't want it to have to be frayed or yielded, for that matter. And so if you look at the graphic on the left, what you see here, this is a splice chuck. The splice chuck is being added to the end of the strand where it was just cut. And then you use the torque stressing coupler. Now this torque stressing coupler is actually connected to another piece of strand that's on the opposite side of the repair. So just imagine I have a strand of a certain length, and I cut the damaged section out. So I have a little nub on the left and I have a little nub on the right. And then between those two, I'm using these two pieces of hardware. And then to actually stress that assembly, there you would use a torque wrench, and then there's a bar that you would put that torque wrench on, and then you would actually torque it. And what it does is it takes these two couplers and it pulls them together. So the net effect is pre-stressing the unbonded section of the damaged strand. The other thing to consider when splicing strands like this is that if you have more than one strand damaged in a certain location, you may need to stagger these couplers because the hardware may be a little bigger than the diameter of the hardware might be a little bigger than the spacing of your pre-stressing strand. So sometimes staggering of the hardware is required. Now, if you remember earlier, I talked about, sometimes you have damage to a tendon, but it only happens in the exterior bay. Now you may say, well, why would that happen? Well, if you have a post-tension slab that's partially below grade, for example, then depending on the protection details at the end anchorage, you may have infiltration of water or contaminants that can otherwise lead to corrosion. So the graphic here that I have my mouse over is an example of a slab where contaminants have gotten into the post-tensioning tendon and corrosion has started to take place. And this corrosion is sort of like cancer. It kind of spreads, over time. And so if this should happen, there's a couple of ways to deal with it. But what I'm going to be talking about is partial tendon replacement. So what you would do, step one, is you would lock off the post-tensioning tendon. And I'm going to describe how do you do that and what that term is. But the basic concept, for the sake of this slide, is that we're going to create an anchor at a portion of the tendon that is otherwise unaffected. That's step one. The second step, and this graphic at the top right is a really good photo of it, is that I would chip open the slab and I would remove those damaged tendons. And in this graphic, you see its full depth from end to end. And then I would put in a new post-tensioning tendon. And then I would pour that back. Now, prior to pouring it back, I would have to put in a coupler. There's two different types of couplers that I want to share with you. One of them is a center stressing coupler. And you can see this coupler has the existing tendon on the left and the new tendon on the right. Similarly, in this other graphic that I have my mouse over, this is also a splice coupler where the new tendon is on, the existing tendon is on the left and the new tendon is on the right. So there's different types of hardware that allow you to connect new and old tendons together. So when it comes to damaging tendons, sometimes this damage is localized and it may not require any remedial action. Concrete screws, cutting, coring, chipping, sometimes the effect is minimal and no repair is required. And in order for that to be the case, the tendon has to be fully grounded. And if you remember earlier, and as I get further into this, I'm going to talk about, is the tendon grounded or not? Because if it is, your repair could be slightly modified. Now, another piece of damage that can happen on a PT slab, and I would say this happens typically, when it comes to bonded post-tensioning, it typically happens during new construction. Rarely, over time, but you can have what we call tendon blowouts. And these blowouts occur at the anchor itself. And so a blowout can happen for a couple of different reasons. One, you could have the bursting reinforcement that's either undersized or mislocated. You can also have low compressive strength, or you just may have poor concrete consolidation in the anchor itself. In my experience, what I've seen the most is actually low concrete compressive strength. That seems to be, if I had to rank these four reasons, I would say low strength probably leads all the other remaining reasons for a blowout. Now, if you have a blowout, what do? You're not going to, demo your slab and start over. You're going to have a local repair. So what you typically do is that you would come in, you would de-stress the tendon because there could be some residual pre-stress force. So remember, you would use either a saw or you would use a torch to release that pre-stressing. And then what you would do is you would chip open the concrete and you would place new hardware. You place your bursting steel, you place any grout accessories that are required, bearing plate, anchor head, etc. And then you would pour back concrete with a high strength repair mortar. But typically you want to have a high early strength on this because when it comes to repairs, sometimes it affects the progress of the remaining construction schedule. So high strength early is important. And then after the concrete hardens, then you would stress these tendons using either a monostrand or a multi-strand hydraulic jack. So next I wanted to shift a little bit into modifying a slab for various reasons, but I'm going to focus primarily on openings and penetrations that weren't planned from the original construction. So when it comes to modifying slabs, I like to break the openings into two categories. One being a small opening, which in my opinion is, let's say 2 feet by 2 feet or smaller. So that's in metric, you're talking maybe 450 mm or less, or larger openings. And there's a lot of different reasons for having these different openings. It could be for mechanical, electrical, plumbing, staircases, or elevator shafts for more larger openings. And the point I want to make prior to getting into this is that you can always modify a post-tension slab, whether the tendons are grouted or ungrouted. There's always a way to do it. You just have to have a contractor with repair experience, and then understand the behavior of your slab. So let's talk about how do you deal with small openings? How do you accommodate them? So the first step that you do is you would use non-destructive testing equipment to find the tendons in the concrete slab. And that's typically done either using ground penetration radar equipment, which I'll talk about what that is and how it works in the coming section, or you can use an X-ray to identify where those tendons are. And once you find those tendons, in many cases, you can shift your openings to the left or to the right just enough to avoid the PT tendon. So this graphic in the center here is an example of that. The blue lines represent the tendon, and then you would just shift your core a little to the left or to the right to avoid those tendons. So for small openings, I would say this would be, the preferred technique. Now, if you hit the tendon, then you need to look at the residual effect in the slab. And I would say on my next slide here, I'll talk a little bit more about how you would do that. So if you hit a tendon, or if you have a lot of tendons affected by large openings, there's a couple things to consider. One is the possibility of shifting it. When I say shifting it, I normally like to think of openings, putting them in the middle third of the slab. Normally the middle third of the slab is going to be the area where it's going to have the least amount of impact to the overall structure. As that opening gets closer to your column strip or to your columns, then you have to consider other effects, maybe not bending, but you may also have to consider punching. So shifting them is always step number one. But step number two is just checking serviceability requirements. After you lock off these tendons around the opening, you would check your service requirements. And then you also would have to check the remaining capacity of your slab. And the thing that's interesting about this concept is that if you create large openings, what ends up happening is that your adjacent bay actually becomes an in bay. And we know from a design standpoint that the bending moment will then increase. So that also has to be considered. The strengthening isn't always required around the opening. In some cases, it actually may be the backspan, which goes from a continuous span to an end span, and the moment increases. Now, I've talked a little bit about locking off tendons, and let me kind of get into a little more detail about how do you do it and why would you need to do it. So typically, if you're creating large openings, you may want to lock off the post-tensioning tendons around that opening. And the reason why I say may is because if that tendon is fully grouted, then theoretically the pre-stress strand will redevelop in that slab, and you just only have to deal with the localized effect. However, if you have uncertainty about the quality of grout, then tendon lock-off may be required. Now, how do you do that? First, you would chip into the slab, create an opening to expose your PT tendon. Then you would peel back the duct, similar in this second graphic here. And then you would use a chisel to remove the grout off the strand. So the net effect is you want to have bare strands. You want to clean them with the wire brush in this graphic that you see here in the middle. And then next you would mix a 2-part epoxy mortar. And then you would fill that pocket with that epoxy mortar. And once it hardens, you've locked off the tendon. And let me explain when we say lock off, mechanically what's really happening here. So the epoxy anchor that's created, it actually has, the load is being transferred due to side adhesion, but it's also being transferred through end bearing. So the combination of these two create a anchorage or otherwise lock off of the post-tensioning tendon. So now I want to talk a little bit about some of the tools to assess the PT slab. And whenever you do an investigation of a slab, there's really 3 basic steps that you would take. First is that you would review all relevant documents, right? And we always say that, having as-built is great to have, having stressing records, grouting logs, doing visual inspection. All of these would be done in what I call the upfront initial review. Now, the second thing of doing an assessment is might require some field testing. And I'll walk you through some of the tools that you can use to understand the performance of the PT. And then lastly could be laboratory testing. In my experience, laboratory testing is quite rare. However, for special cases, you may need to, take coupons of your strand and actually send it to a laboratory, either to do chemical testing, or you may have to do some tension pull tests. Now, before I get into the different techniques, let me explain why you would do this assessment. In many cases, when an owner buys an existing building, one of the things that always happens is he hires a consultant, like many of you are on the call, and he says, I want to understand the condition of my structure. And the default, repair, or the default action is structural assessment, understanding existing conditions, and understanding, how the load path, and understanding the load diagrams, and checking members to ensure that they're adequately designed for those loads. But one thing that's often overlooked in my experience is understanding the durability side of your structure. And I'll talk a little bit about, ways you can do a durability check, but focus on the post-tensioning tendon. So if you're doing a durability check on your post-tensioning tendon and you start with the visual inspection, the first thing that we always do is we go to areas where you would expect distress, having full knowledge of how a post-tensioning system behaves. So one, you would look at the high and low points, right? And the reason I say that is because that is where the contaminants have the shortest distance to get to the pre-stressing strand. I would also look at the anchorage zones. If I have a pour back that's improperly done, or if I have poor detailing at the perimeter of the building, this could be an area of distress. Any part that's below grade, I would always check there because of the possibility of contaminants coming through or leaching through the wall. I would look for cracks, falls, efflorescence, rust staining. Anywhere that there's a water feature, above the building, I would look directly below that. That's a good place where there could be some challenges if the waterproofing has failed. If you have exposed strands or ducts or tendon failures, or even previous repairs, whenever we're doing a visual, it's really easy to just look at those areas that were patched before. If it was not a good patch, then that tendon in that patch could be in serious distress. And then the last part is excessive deflection. So these are things that I would do step one when I'm doing a visual inspection of a structure, just to kind of understand the health of the post-tensioning tendon. Now this slide has a lot of information on it, but I want to break it down in simple terms. There are a number of non-destructive test equipment available in the marketplace to help you understand the health of your post-tensioning tendon. Now, when I prepared this list, I would say, the focus on this part of the industry has really came about probably in the last 10 years. So in the last 10 years, this list, we populated this list based on existing technology and new technology. Now, when it comes to doing an investigation, I just want to make one caveat here. You would never use all of these techniques. Never in my career have I used all these techniques. What you have to do is you have to understand the pros and cons of each technique, because there is no single non-destructive test equipment that will give you the full picture. It does not exist. So what you have to do is you have to pick and choose different techniques to help you understand the health of your structure. Okay, so let me kind of walk you through some of the techniques that I've seen used in my experience. Now, the first one here is borescope camera inspection. I really like this, and I always start with this when I talk about testing equipment, is because this is a way of visually seeing the condition of the strand, the quality of the grout, or the presence of grout, or the lack thereof. And the way that you would perform this inspection is that you would drill a small hole, let's say 25 mm bit is max size, and you would use a special bit and you would drill into the slab or to the wall or to the beam, and there would be a depth indicator on that drill. So basically you combine your as-built drawings, you set your depth indicator on your drill, and you drill a small hole into the concrete. The next thing that you do is that you would insert a borescope camera. Now, this is the same camera that's used a lot in the, let's say in the medical field. It's a lot smaller in the medical field, but the concept is the same. Basically, you have a really small camera on the end of a wand, and that camera has articulating capabilities, meaning that it can spin to the left, to the right, upside down, and around. Now, if you drill into a tendon, the graphic on your far right is what you would expect to see. So what do you see here? You see a drilled hole, and you see duct, the metal duct, and then between the duct, you see grout. That's what you want to see every single time you drill. However, in my experience, what I've seen is that that's not always the case. You could have tendons with no grout, which is the second picture from the top, or you can have grout that has settled over time, and I'll explain shortly how that might happen. But this technique I really like because it tells you information firsthand, and you don't have to interpret results. Seeing is believing. The next technique is X-ray. So, and I really like the X-ray for this very reason. An X-ray will tell you exactly what's in the slab. Again, no interpretation required. However, that comes with a few limitations. Number one, an X-ray requires a radioactive isotope. So just imagine, going into their X-ray room at a hospital and turning on the switch and just standing there for hours. That's a bad idea. So basically, you have to have certain distance away from this radioactive isotope when you expose it to a film. So there's a safety issue. And then the other thing is that it uses bulky equipment, probably the size of a small refrigerator that you may have used in college dorm, for example. And then on top of that is that the viewing area is limited to the size of the film. In my experience, I've probably seen maybe 600 mm by 600 mm is the maximum size of film that I've seen in a single shot. So you can imagine if you need to X-ray a large area, it could take you days, even weeks, to get the full picture using this technique. Now, the other technology that's come about in the last, I would say, 5 years, magnetic flux leakage. I actually had a professor from graduate school approach me about this technology, and it's a really good technology from a science perspective, but it has some limitations. But let me kind of walk you through how it's used. It's really cool technology. So we know pre-stressing strand, that's the steel wires are ferromagnetic material. Okay, so what does that mean? That means that I can magnetize the steel, and I can magnetize it to saturation. So what happens, if you remember from your physics, I remember in college, physics 2, we took classes on electronics and magnetic fields and so forth. And when you magnetize steel, it creates a magnetic field. We call that magnetic flux. So the basic concept here is that your magnetic flux is actually proportional to the cross-sectional area of the steel. So what does that mean, Clyde? What that means is that if I take a sensor and go across a tendon that's fully magnetized, I can use that sensor to measure the change in magnetic field. If there's a drop in the magnetic field, that tells me that there is a point of smaller cross-section at that location, which signifies a defect. So this technology is really cool, I've seen it used on bridges. I've seen it used in some building applications, but it all deals with creating a magnetic field and magnetizing the strand and checking for a change in that magnetic field. The other one I want to talk about is ultrasonic tomography. And when I talk about ultrasonic tomography, I always like to go back to impulse echo. A lot of you may remember the term or heard the term impact echo. So impact echo, if you look at this graphic here, impact echo, what it does is it sends a signal into the concrete, and that signal reflects back when there's a defect. And the way we know the depth is we measure the time it takes the signal to reflect back. Now, the challenge with impact echo is that it's just a single pulse. So there's a single point of data. However, what has happened over time is that they've taken impact echo and they created a head that has a whole bunch of sensors on a single head. So if you look at the graphic on the bottom left, this is that head. So that head has all these sensors, 20, 30 sensors. And what it does is one sensor sends a signal into the concrete and then it reflects back. That's how it works in one shot. But what's happening is that all of these sensors are working at the same time. So you're collecting an enormous amount of data that can help you understand the thickness of the material, if there's cracks or delaminations, if there's impurities, and you can actually convert that data into a 3D image. So this graphic on the right kind of shows you a tendon that's fully grouted, represented by green, and then the red would actually represent a void within that specific tendon. The reason you would do this is because you're trying to find a quick way, a non-destructive way of finding the problems without making Swiss cheese out of your slab by drilling a bunch of holes or doing a lot of chipping. Now, the last technique I wanted to talk about is acoustic monitoring. And acoustic monitoring is a really interesting technology. If you're like me in graduate school, you work with a lot of different sensors and low displacement transducers and string pots and rotation meters and accelerometers and so forth. So I remember this from my grad school days, and I wanted to show you how this accelerometer can be used to detect wire breaks. So we know for wire breaks, if a strand is pulled under tension, and there's a lot of energy stored in that strand. Now, if a wire breaks, or let's say the whole 7-wire strand breaks, you release a lot of stored energy. Now, when that happens, that energy, two things happen to that energy. One, it's reabsorbed into the surrounding concrete, or two, it creates an acoustical sound or vibration into the slab. And so if you have accelerometers on your slab in strategic locations, then the accelerometers can actually detect the acoustic waves in the form of surface vibrations, and it can help us triangulate exactly where the wire break occurred. So it's a really cool technology. I've seen this used on stay cable bridges. I've seen it used on historic buildings. I've seen it used for long-term owners who have had problems, who want to get a handle on the possibility of future problems before it becomes a safety hazard. Okay, so the last topic I wanted to talk about is PT grouting defects. And I want to talk a little bit about, how it happens, and then what do you do if it happens. So to introduce this topic, first I want to talk about how do you grout a post-tensioning tendon. And I want to talk about the mix design. So typically, the mix design consists of cement and water. And the water to cement ratio is normally around 0.45. Now, what normally happens for a post-tensioning tendon is that you would pump grout from one end of the tendon to the other end. So if you look at my screen here, you see this, this blue line represents a draped tendon. And when you do pressure grouting, you have to have an inlet and an outlet. And depending on the amount of drape, you may have high point vents. So what happens here is that if this were a slab, what I would do is where my mouse is, I would mix grout and I would start injecting here. And then that grout would go down to the bottom, just follow my mouse, and then it'll go up to the top at the high point. And then what happens when that grout reaches the high point, it rushes down to the bottom of the next span. And then it slowly starts to backfill, just like you see my mouse. It's backfilling to the left, backfilling, backfilling, backfilling. And what happens here is that air is trapped within that duct about 1 meter downstream of the high point. Now, we've seen this in a lot of different cases. We've done, and this is across the industry, it's not just it's that the industry has looked at simulating draped tendons with clear duct, and we've grouted tendons just as I described. And time again, for basic grouts, they find that air is either trapped at the high point or 1 meter downstream. Now, if you have a grout vent at the high point, you can open the valve and release the trapped air. In the post-tensioning world, we call this burping the tendon, okay? You're actually releasing trapped air inside of the duct. And many, on some projects, you may have high points, but it's very rare that I've seen a project where there's another high point vent 1 meter downstream, where there's a second possibility of trapping air. So that's one way you create what we call voids inside of a duct, okay? Is the grout actually rushes down and then it creates a void at the high point. The second thing is that if you grout too fast, you can trap air. And you may say, hey, Clyde, how does that happen? Well, if you grout fast, what happens is you create turbulence inside of the duct. And just imagine like a wave on a beach. The wave comes crashing in and it traps air, right? It curls over itself and the air is trapped underneath. Well, similarly, the same concept happens for grouting. If the grouting crew is in a rush and they grout too fast, you can trap air, and that would be locked inside of the tendon. Okay, so these are a couple of reasons why you would have trapped air. The other thing I want to talk about that leads to trapped air or voids is the grout material actually segregating. And let me explain how that may happen. So if you see this graphic here, I'm waving my mouse over it. This is an inclined tube test that was done in a laboratory. And what you see here, this is a draped tendon, and you're basically simulating a tendon that has a low point on the slab and a high point at the top of the tube, okay? So I would say this is quite a bit of drape, but it actually makes the point that I'm trying to highlight here. What we found out is for basic grouts, the grout material has a tendency to segregate. And what I mean by segregate, it starts to return back to its separate constituents. So the cement can separate, from any admixtures. And this graphic you see on the top right, this is an example of segregation, okay? And this murky water you see at the top, this is what we call bleed water. And you may say, well, Clyde, how does bleed water happen? Where does that come from? Well, just imagine a vertical column of grout. We know that there's head pressure, right? The taller the column, the more head pressure. So what we have found is that the grout is heavier density, and it's actually pushing down on itself, and the bleed water is rising to the top. So this is how that segregation happens. It's not because they didn't mix it properly. It's not because they put too much admixtures. It's actually that the head pressure causes the grout to segregate, and bleed water is left at the top. Now that bleed water can do one of two things. A, it can remain in the duct, or B, it can reabsorb back into the concrete, causing a higher water to cement ratio in that region where the grout quality is poor and it's like a chalky material. Now in a duct, you may say, okay, but how does this bleed water actually rise to the top? Like I'm having a hard time processing it. Okay, well, it happens two ways. One way is that, remember the 7-wire strand? It has this interstitial space. Well, those little small spaces work like capillary tubes. So what happened is the bleed water actually wicks up through the strand and accumulates at the top. So that's how it's accumulating at the top. And another way to see how it goes to the top is that at this bottom right-hand graphic you see here, this is showing you a bleed trail inside of a duct. So just imagine the water is rising to the highest point in the duct and then to the highest point of the duct. And so what you see here in this graphic, you see that there's porous grout in this bleed trail, and this is changing the quality of the grout within the duct itself. And the pH of the grout is also reduced at this location, which means the protection of the steel is reduced at the location. So the point I'm trying to make here is that bleed water, which can remain in a duct, or bleed water that can reabsorb into the grout, can lead to voids inside of the duct or poor quality grout inside of the duct that can create a path or a an avenue for contaminants to get to your pre-stressing steel. And we know when contaminants get to our steel, what happens? We have corrosion, and that leads to other problems. So let me walk you through a quick case study to kind of share this with you, because I know when I talk to consultants about this issue, they say, okay, Clyde, well, that's a field problem. I'm not a field guy. I'm going to hire the PT guy. He's going to do a good job. Finish, no problem. I say, okay, we can assume that works. However, if you're asked by the owner, or if you recommend to the owner, hey, you're buying this building, you're doing a tenant conversion, or you're buying an abandoned building and you're putting another 20 floors on top. Hey, Mr. Owner, does it make sense to do a durability check on your slab that could include PT investigation? And if the answer is yes to that, let me share with you what would be a process that you can use if that's your task. So this case study I'm going to talk about, it's a residential tower. It's on Ream Island. And the B2 level is a raft slab. It's conventional rebar, which is pretty common. And then all of the remaining floors are post-tension slabs. And I want to highlight that, you know, there are parts of the slab that are below grade, okay, which is, you know, the root cause to the problems that I'm going to share with you. But I'm going to focus primarily on what is a consultant, what do you do, how do you start, where do you go? Okay. Some of the observations here in this particular structure is that there were cracks in the slab due to restraint, there was falling, PT in different areas was either exposed or highly corroded. We actually even saw some empty ducts, which was quite a surprise. So, investigation. You're the consultant on the job. Where do you start? So, as I pointed out earlier, you know, tier one, or step one is always, you know, understanding the structure, doing a visual, and then combined with that, you do some non-destructive testing. Okay, what's the non-destructive testing? Okay, so that's hammer sounding, right? We can use acoustical hammer sounding to find areas of delamination. Age-old technology, been around forever. You can also use ultrasonic pulse velocity, which I showed you earlier, can help you detect areas where there's, let's say, medium to large size voids. I wanted to highlight that. Small voids with that technology is one of the limitations. However, for medium to large, ultrasonic pulse velocity is a good technique. So that's step one, and you've done that. Okay, so you collect your data, and then you say, hey, there's some other areas. I want to go a little bit deeper. You know, this is just, you know, preliminary. Let me go a little bit deeper to understand really what's the health of my structure. So tier two is when you would do what I call semi-destructive testing or minimally invasive testing. So what would you do? GPR is a really good tool, right? Can help us identify defects within the slab. The borescope camera inspection, to me, it's a go-to technique. It's inexpensive and it tells you a lot of information, and you don't have to be a scientist to interpret the results. You could take some cores, right? You can also do some chemical analysis of the cores and the PT grout. Now, I want to highlight this. You need to check the quality of the grout. You could have a tendon that's surrounded in chlorides, but let's say the chlorides are below the level of corrosion initiation. But we know over time that could change and that can lead to problems down the road. So always, like, you know, if I'm going to drill into a tendon, I might as well collect some dust samples and check for chlorides. And then the third step is really compiling all of that data and preparing a report. Now, what does that report look like? Let me give you a couple takeaways that are really good documents to put inside of your report in addition to your own conclusions. One is developing plans that really show the condition of the tendon. And this graphic you see on the right here, this drawing, this is really interesting because it tells you for every tendon what's going on. You not only have crack napping, but you also have for each tendon if there's grout, no grout, corrosion, broken strands, broken wires, etc. So this is really good document to prepare for a tender package because it really paints a clear picture to the contractor, you know, what are the problems and what are the extent of the problems. Additionally, in your report, you would have a summary of your visual findings, and it's shown in the graphic on the far left-hand side. Now, that would be your report. But when it comes to repair, I always like to, you know, explain a little bit further for consultants, because if you're going to have a good contractor, you should have some knowledge, some peripheral knowledge of what's going on, what do you do, and how is he fixing it? Just as a logic, sound check, if you will. So if you have severe corrosion, remember earlier in my presentation, I said, hey, you can do partial tendon replacement, okay? That was chipping open the trench, take out the bad PT, put in the new one, finished. However, another technique that I've seen used is that I'm going to lock it off just like you explained before, but then I'm just going to convert that slab into a conventionally reinforced slab. That's always an option. In some cases, may be easier because you don't have to consider the effect of stressing a tendon and having proper access to stress that tendon. So think of this as always a technique is that, hey, I can take out the bad tendon and I can simply replace it with a mild steel reinforced concrete slab. Now, when it comes to grouting voids, there's a couple of different techniques that I wanted to share with you, just to give you, again, a little bit more knowledge into the contractor world. There's a couple of different techniques for filling voids. I would say primarily there's two, just to make it plain. One is pressure grouting. What's pressure grouting? The same technique that's used to grout the tendons from day one. You have an inlet, you have an outlet, you pump material from A, it comes out at B. You keep pumping it until the material coming out of B is smooth, free-flowing, without any lumps. Shut off your valves, finished, okay? But there's another technique called vacuum-assisted grouting. And I'm going to talk about that on the next slide. But whenever either of these methods are used, there are standards that I want to share with you that are good resource, for having a deeper understanding into these techniques and how they may be applied. The Post-Tensioning Institute, based out of the U.S., has a really good document on grouting, and I would recommend it as a reference. Now, in all these graphics that you see here, what this shows you is just, different stages of remedial grouting, where you're installing new grout ports, you're mixing equipment, you're connecting your hoses and making sure you have good flow out the other hoses. Now, I want to talk just briefly. This is my second to last slide, just to give you a sense on a time check here. Remedial grouting using vacuum-assisted grouting technique. Now, let me explain why I would want to use a vacuum to help me with filling a void inside of a duct cast in concrete. Now, number one, these voids can be quite small, right? Just imagine a round duct, let's say it's 75 mm, 100 mm inside of a beam. Flat duct, you're talking about, 1 inch by 3 inch. So that's 25 by 75 mm. So a flat duct, the void would be small. The duct is already small. So if you have voids inside of these ducts, sometimes it's difficult to push new grout material through the small space inside of the duct. And you could build a lot of pressure trying to do that. So the concept here, and this graphic is worth 1,000 words, is to use a vacuum to help you with the grouting. So just imagine you have this beam here. This tendon represents a beam or a slab for that matter. So I have a grout pump on the far right, and I'm using positive pressure to fill that tendon full of grout, okay? On the other side of the tendon, what I'm doing is I hook up a vacuum pump, okay? And the basic concept is the vacuum is actually creating negative pressure. We're actually sucking the air outside of that void inside of the duct, while the pressure grouting is pushing the grout inside of the duct. So it's basically taking material and it's pulling it through those small spaces to make sure the tendon is completely filled. So this technique, again, is called vacuum-assisted grouting. I've seen it used in various occasions. Primarily if you have a tendon that's partially grouted, this is when I see it used. If a tendon is completely voided, pressure grouting is definitely the way to go. So in summary, just to put all of these four or five different segments together, number one, PT tendons can be modified to accommodate openings and penetration. while that might seem obvious in certain industries, there's sometimes aversion or apprehension about using post-tensioning in certain structures because, you know, when you think of a tendon, it's inside of concrete, it's stressed, if it breaks, you know, what happens? If I'm in a hospital and a tendon breaks during a surgery, it could be a disaster. You know, so sometimes owners believe I can't modify a PT slab. I got all these tendons 1 meter on center with an orthogonal grid, and where do I go? There's no place to cut. But the answer to this is yes, you can modify any slab for openings or penetrations of any size. Number two, filling PT tendons with basic grout can lead to grout voids and subsequent corrosion. However, if you detect it early, remedial grouting is a possible solution. Just to comment about this, as I talked about a little bit earlier, the basic grouts have a tendency to bleed, and that bleeding increases with break. That bleed water can stay in the tendon, or it can reabsorb back into the grout. If it reabsorbs, you have a void, and that void is a potential avenue for corrosion agents to get to the strand, which can lead to problems. So the real question is do you have voids? And if so, you need to find them as soon as possible, because it could start with a small problem and it could lead to something much more serious. Thirdly, PT tendons can blow out or fail if they're partially or fully ungrouted. And how can that be? Again, the corrosion protection is gone, contaminants get to the strand, and for that unbonded or partially, grouted section of tendon, when it releases, it's like cutting a rubber band. The force will release and it could be damaged in the immediate area. Fourth, there's no single NDT method that can accurately assess PT tendons. I'm just telling you that with experience. There's no smoking gun that can take care of all cases with high precision. All pieces of equipment have pros and cons. It has advantages and it has limitations. But using a combination of different techniques can give you a good health check of your post-tensioning. Next, partially or full replacement of bonded tendons can be achieved with specialty hardware. And I showed you some of those different gadgets, stressing couplers, different type of hardware that allow you to connect tendons together. Different manufacturers have different systems, but generally they all work the same when it comes to coupling strands together. And then the last comment that I have here is that an experienced designer and a good quality repair contractor is required to have a successful PT modification or repair project. One thing that I've learned in my experience in the 20 years being involved with post-tension concrete is that there's not a lot of repair guidelines, specifications, manuals, or books on how to modify PT structures. And if you have to do it, how do when do you do it? When do you not do it? It's still a bit of a black box. That's the point I'm trying to make. The Post-Tensioning Institute is trying to develop, some guidelines for this field. I would say a lot of experience has come through years with PT subcontractors. However, as consultants, I think you have a responsibility to have some knowledge of what's practical and what's not. Further, it's good to have some knowledge about different tools for assessment, because all structures, can't be just checked with structural analysis. Sometimes durability assessment is also required. So to conclude, I just wanted to wrap up by saying I really appreciate you for tuning in. I understand it's a little after 5. Hopefully you found this information useful. I've tried to take, 20 years of experience and kind of, do a high-level summary into, 60-minute presentation. But I'm certainly happy to, to follow up with you separately if interested. And thank you very much. So just to close out, what I'll do now is I believe we'll take some questions, and I think Karam, I think you're going to help me facilitate that. So thank you very much, everyone.
Thank you, Clyde. Thank you, Clyde. And I also wanted to thank everybody for joining us. Again, I hope that it was a good utilization of your time. Before we get into the Q&A, I just wanted to remind you again is that once you actually close the Zoom session, there will be a pop-up window that contains a short survey that would truly allow us to better serve you in the future. So we truly appreciate if you take a couple of minutes just to fill that survey. One more thing that I want to remind you of is that tomorrow we're actually holding the final strengthening webinar by Jay Thomas at 4 p.m. Dubai time. If you haven't registered yet, we'd appreciate if you go there and register. So Clyde, we'll get to, we have about 25 or 30 questions. We'll try to answer some questions.
Okay.
The first question asks about, in one of your slides, you talked about one of the ways or means to basically fix PT structures is by opening a trench and either replacing the full tendon.
Mm-hmm.
Now, with doing that, will you be damaging any, either the top steel mesh or the bottom steel mesh? And if the answer is yes, how can you solve that?
Right. Okay. Good question. So the question, right. So the question is, if I have to replace a tendon, how do I deal with the mild reinforcement? So normally what's done there is that you would chip around the mild steel, and you would not damage it. So generally speaking, when I've done this type of repair, I have been safely able to chip around the existing steel, leaving it intact and in place, undamaged, and chip down far enough to get to the tendon, remove the surrounding grout, and then pull that tendon out safely without damaging any other remaining reinforcement.
All right. The next question talks about it. If you have an existing slab, the PT slab, and you want to open an opening, is there a minimum distance that is required for you from the edge of the opening to the PT tendon locking you're doing to the existing PT?
Is there a minimum opening? Is there a minimum distance required from the opening to the tendon that you're locking off?
Yep.
No. So okay. So let me answer two ways. Number one, if I lock off a tendon, there's no minimum distance. So what I would do is I would remove concrete up to a good section of the tendon, and then I would perform the lock off there. So there's no distance. You would just find a good portion of the tendon, create your opening, pour in your, clean your tendon, remove the grout, etc. And then you would pour in your epoxy, create your lock off. So there's no minimum distance. Once you create the lock off, then your tendon is theoretically locked off there. And from that point beyond, you can do, full removal. So there's no minimal distance.
Okay. Another question asks whether we can use FRP systems instead of the replacement method that we've discussed in this presentation. And in that specific question, they talks about overpass bridges specifically.
Right. Okay. So can we use FRP systems in lieu of tendon replacement? So I would say, categorically speaking, the answer would be no. And the reason for that, and this was covered by Dr. Tadic in some of his presentations, is that carbon fiber is used as supplementary reinforcement. We know when we design a PT system, this is primary reinforcement. So generally speaking, if I remove the full length of a tendon, you cannot replace it in kind with carbon fiber. Now, let me say it a different way. Now that was general. Let's get more specific. If I have a slab that has, 10 tendons within a slab, and I take out one tendon, what I would do is, as opposed to replacing that one tendon, when I say take it out for whatever reason, either it's cut or it's corroded, okay? And instead of putting it back, can I use carbon fiber? So in that case, if I lose one tendon out of, let's say, 10, so it's a 10% reduction in capacity, just in round numbers, yes, that is within the limits of carbon fiber. So the response varies. It truly varies. It just depends on how many tendons are affected and what the remaining capacity is of the reinforcement that's in that section, and if it's beyond the limits of carbon fiber.
All right. Next question asks about stressing of tendons for new construction. What does the code tells you about the percentage of strength of concrete before you actually stress the tendon?
Okay, good question. So typically when you're doing stressing of tendons, the concrete needs to reach a certain compressive strength. Generally speaking, the rule of thumb is 75% of the 28-day strength. So it's 0.75 of F prime C. That's the rule of thumb for when concrete is considered cured, enough for stressing operation. And then what happens with that same strength, the PT subcontractor actually uses that same number in his general zone and local zone reinforcement calculation. So the idea is that the two are aligned. The guys on site know when to stress based on concrete strength, and then the guy doing the calculations for bursting reinforcement knows what the minimum strength will be used for stressing. So that's how the two stay aligned. There's no blowouts.
Okay, you talked about PT grouts. The question asked is these PT grouts, what are they based off? Is it cementitious or epoxy? And there's another part to this question is that are there any additives that you can add to the grout itself, and are they harmful?
Right. Okay. Good. So the post-tension grout is a cementitious grout. Basic grouts are considered, Portland or cement and water. Now, so that answered the first part. They're not epoxy modified or it's cementitious grout. Now, the second part is, are the additives harmful? Applying the right amount or right type of additives can be used. In many cases, in my experience, additives are added. So yes, it's a good thing. However, we know, too much of a good thing can lead to a bad thing, right? It's like baking a cake. You put in the right amount, it tastes good. If you put too much, it tastes horrible. So yes, you can use it, but you have to know what you're doing, and you have to you have to do it within the limits of the material that is designed.
Okay, you also talked about the vacuum grouting, and the question says that suction will definitely help in avoiding any airs. However, it might cause some segregation. So what is the proposed ratio between the negative and positive pressure used during the vacuum grouting procedure?
Right. Okay. So that's a good question. That's a really good one. Okay. In all of my experience doing vacuum grouting, man, I've never seen segregation of the grout material. And the reason for that is that, well, one of the reasons is that you're not able to achieve a perfect vacuum, right? We know a perfect vacuum is, I think it's 30 inches per inch of mercury, if I remember correctly. Okay, so you can't achieve a perfect vacuum. Why is that? Because you have metal duct that's corrugated inside of concrete, and at the seams, air leaks. Okay, so you can never achieve a vacuum, the perfect vacuum. So therefore, what you're pulling, the amount of pressure on pulling is, it's just enough to help move that material through those really tight spaces. So I haven't really done a calculation on positive and pressure and to see what the relationship is between the two. That's something I haven't thought of, but I would say from a practical standpoint, essentially what we're trying to do is move material through a small space. And if you can have something just tugging on it just ever so much, it can help it get through those tight spaces. So that would be my response to that. I really haven't looked at pressure differentials between positive and negative to see if it creates challenges, but I have never seen, I've been doing remedial grouting for 10 years. I've never seen a problem doing it, ever.
Okay, we'll go to the last question, in which it says, you also talked about a replacement of existing PT tendons so when you do that, you're actually putting a trench, and it talks about what makes you sure that you're going to have a good bond between the old concrete, the parent concrete, and the new concrete that you're going to be putting after replacing that tendon.
Right. Okay, good. So when you're doing the trenching, you're expecting, okay, so that's a good question. How does the new and old concrete work together? How do you know it's going to be, working monolithically? Okay, so I think of it just like doing any other, good concrete repair, right? Number one, you have reinforcement that is, sticking out of the existing concrete. Okay, that's number one. Number two, if you think that that reinforcement could be light and you want to enhance the shear friction, then you can increase the number of dowels going into the existing concrete. That's second. The third thing is that you would roughen the surface of the concrete, of the existing concrete, with a concrete surface profile to, let's say, a 6. So the way that the two work together is through a roughened surface and through reinforcement designed for shear friction. Those two will enable the new and old concrete to work monolithically.
All right, Clyde, thank you so much. And I, again, wanted to thank everybody who joined us today. We hope that it was a good utilization of your time, and we hope to see you tomorrow in our final strengthening webinar. Have a good evening, everyone, and Ramadan Mubarak again. Thank you.
Okay. Thank you very much, everyone. Appreciate you tuning in.
كده لازم